Welcome everybody. My name is Peter Kolusny, and I will be the instructor during this another view lecture from iPexpert. Today we will spend some time talking about NAT on the Transparent ASA. So as we probably all know, the ASA can be deployed in one of the two firewall modes, routed and transparent, which ultimately affects how the firewall handles the packets. When we enable the routed mode, the ASA is going to be routing the packets between the interfaces. The interfaces will be configured with different subnets, and before the packet is serialized onto the link, onto the new local network, the device is going to re-encapsulate the frame, changing the source MAC address inside. When we run a transparent ASA, the device will be acting more of as a bridge or a switch. It is going to be switching the frames based on the content of the CAN table, normally without changing any type of addresses in the frame. So one could say that when you enable ASA in the transparent mode, no routing information is needed by the firewall, so it can operate and so the communication can be established between the devices that are separated by our transparent ASA. But this is actually not the case. So there are at least two different situations when the ASA is supposed to know route information, it is supposed to have its routing table populated. One is when the ASA is originating the traffic, like it wants to access, reach syslog, AAA services, syslog servers, which are located in a remote subnet. So those devices are not part of the local, let's call it transparent network, and the ASA still has to know how to reach those subnets. And the other case, which is going to be the focus during this session, is when the ASA is configured to perform network address translation in the transparent mode. So as we will see now, if the ASA is going to need those routes or not will depend on the type of configuration we are dealing with. There will be 4 different types of NAT configurations that actually depend on 2 different things. One is going to be if the pool, the address pool that we use for translation, is part of that transparent network. So in other words, if the addresses that we use to translate the packets, if they are part of the local subnet or not. So if the pool is local or a non-local. And the second is going to be if the client or the device that is subject to the translation is part of the local subnet or not. So this is what I will be doing today. I will show you how to configure the ASA depending on the type of network and the configuration that we want to do for NAT. So as I said, there will be 4 different cases. Once again, we will start with a pool, NAT pool that is going to be part of the local subnet on the ASA. So the one that is configured, the pool that is part of that transparent network configured on the devices that are separated by the transparent ASA. So I'm going to call it a local pool. And we have 2 options over here. One is, as I said, if the client is going to be part of the local network or a remote subnet. So the source, or just the client, is a local device. And then source is part of the of a remote subnet. And we will have similar subcases I would like to discuss for the second option when the pool is going to be non-local. So non-local IP address pool. So these are the addresses that we will use to, after translation, the post-NAT addresses, and the same sub-options here, local client and remote client. So the client here is basically going to be the device that we want to change the address for. Now, I will be extensively referring to the topology, which is really straightforward. We will have just 3 devices involved in this network. Router 10 is going to be connected to the outside of the ASA. So ASA 4, this is our transparent firewall. Router 5 is going to be connected to the inside. And we will also have a remote subnet, which is going to be 10.5.5/24. Where the local subnet, so the transparent firewall subnet, the subnet between router 10 and router 5, this is 172.10.40/24. So this is outside, this is inside. The ASA is pre-configured as a transparent firewall. It is configured with stuff such as access lists, so it allows ICMP communication. Router 10 and 5, they also run EIGRP. So maybe let's first, before we configure any type of translations here, let's first take a look at the regular communication when there is no NAT involved in the process. So I will go to router 10, and I will simply try to ping to access router 5, which is located on the inside. So we see that we have connectivity. The packets are flowing for the ASA. Now, on the ASA, what's going on from the ASA's perspective, what the firewall is doing so that this communication can be actually established, it is internally, and maybe let's first take a look at the configuration of the bridging groups. So we have just one bridging group defined, number 1. It is associated with 2 physical interfaces, and the firewall's address is 172.10.40.40. So this is basically, this address is part of our transparent network. And those 2 interfaces, as I said, one is configured as outside, the other one is the inside port. So when router 10 wants to talk to the device that it thinks it's connected to the local subnet, it internally looks at the ARP table because it knows that this device is locally connected, and it tries to find a matching layer to address so it knows where the frame should be sent to locally. So 10 initially sent some ARP request messages, 5 replied, this stuff is allowed for the ASA. It was able to populate its ARP table. So the frame was going to be destined locally to this MAC address. Now, since those devices, router 10 and 5, they are part of different VLANs, so they are configured to be part of different VLANs and layer 2, this is just to make sure that the traffic is always going to be flowing for the ASA. Because if they were part of a single VLAN and connected, for example, to a single switch, then the devices could talk locally bypassing the ASA. So obviously in our network, the VLANs on both sides are different. We've got VLAN 10, VLAN 5. The packets are going for the ASA. So ASA gets the frame and internally looks at the content of its CAN table. So before it is able to switch the frame and apply the inspection and any other configuration we have we have done on the firewall. It is going to be looking at the CAN table to find the outgoing interface. So the MAC address in our case is this one, which we see is found on the inside interface of the ASA. This one is the MAC address of router 10 connected to the outside. We see we've got two additional MAC addresses that are now part of the CAN table. And these are the addresses that are that correspond to the switch ports. If I were to show you the capture, maybe let's take a look at the capture on the ASA. The reason that ASA populated a CAN with the addresses of the switch ports is that the switches generate things such as BPDU, CDP messages, so it also learned about those addresses and put them into the CAN table. But obviously in our case, what is going to be important will be just those two addresses. But just to show you that it's actually the switch, what we've got over here, and we will take a look at the output of the capture with the headers only option that is going to show us the also layer 2 information. And let's take a look at just one interface like inside, and let's say real time with a detailed option. Just a couple of frames. So obviously the packets that start with a destination MAC of 01005E and then A at the end, this is IP protocol number 88, so EIGRP. So I said the router 5 and 10, they run EIGRP, and we see that they have established an adjacency with each other. But this stuff, 0180C2, it says 802.free encapsulation, and specifically this is the BPDU frame generated by the switch. So this is why with just two devices shown in this logical diagram that are part of our transparent local subnet, we see 4 different MAC addresses in the CAN table of the ASA. But again, in our case, we will focus just on these two. So router 5 and router 10. So once again, 10 sends the frame to this destination MAC, which it thinks corresponds to router 5's logical address. ASA gets the frame on the outside, does the CAN table lookup, and knows that the frame should be sent to router 5. It doesn't change layer 2 addresses, it doesn't modify layer 3 addresses, it simply bridges the frame to 5, 5 replies, and it uses the same process to figure out where the frame should be sent to 10 this time. So it is going to receive the frame on the inside from 5, send it via the outside to router 10. So this is what happens when there is no NAT configured, and this is also going to be the case when the device is trying to reach a remote subnet through that transparent ASA. So let's try to ping 10.555, which is the loopback address of router 5. The loopback here is used to emulate the remote subnet. So once again, this is the local subnet, or just the local network, where this loopback is going to be our remote subnet. So even the now destination, layer 3 destination address in the frame is going to be 10.555, and ASA doesn't know anything about 10.55/24, we see that the traffic is still flowing through the firewall. And this is because before router 10 sends a frame to 10.555, it internally says show IP route to figure out what is the next hop, it sees that this is my next hop for this subnet. This is directly connected to my gigabit Ethernet interface. So I will take a look at the content of the ARP table and send the frame to this next hop locally. So ASA doesn't even bother with checking the layer frame information. It simply bridges the frame. Once again, it has an entry in the count table for this layer to destination. So no layer free routes are configured on the ASA in the routing table. Once again, routing table is blank. We see that the communication is working. So what is going to now change when we start adding our network address translation configuration? So in the first case that I want to show you, which is the local pool, we will now focus on this scenario. When once again the pool I will use to translate the addresses is going to be part of the transparent network. And we will specifically take a look at this first option here, when our client is a local device. So let's take a look at this. And the device that is going to act as a client here is going to be simply a router 5. But this is going to be that interface. The interface that is part of 172.10.40/24. So I will be trying to translate 172.10.45, let's say, to something from the local subnet, 172.10.55. So this is my client, and this is the translated address. And I will use the ADONET configuration. This is going to be a static translation. It doesn't really matter what type of translation you configure because the logic is going to be still the same. It will only affect the static versus dynamic translation. In this case, it's only going to affect what device will be able to initiate a session. I will be showing you the examples with static translations, so the pool is going to be a single IP address, but once again, it's not really important. Yeah. So let's create an object for the original address of router 5, 172.10.45. This is the original address of router 5, part of the transparent network. And now the translation, inside, outside direction, and the translated address is part of the same subnet. So it's part of the local network. I said that this is going to be .55. So we can take a look at the details of the translation. And this is the original address and the translated one. So now on router 5, I can reach the router 10. Since this is a static translation, on 10, I should be also able to reach 5. 172.10.40.55. So I'm trying to reach the translated address. And we see that we have connectivity. Okay, so what happened internally is that, well, the question is, how does router 10 know what device the frame should be sent to when it wants to reach 172.10.40.55? So what is the local address that corresponds to this IP address? And if we take a look at the ARP table here, on this device, we should see an entry for 55. Let's say, Okay, so there is a translation. This is a static translation, so it is part of the XLA table. It will never time out. And what's the, say, show run object 5. And we see that we've got the hits over here. We should see okay, let's say show run include route. Okay, I've got a bunch of static routes that I have defined previously when I was testing this, so let's take them out. It shouldn't be the case what we have right now. I just wanted to show you what's going to happen before we start playing with feature known as proxy ARP. So once again, at this point, we should have connectivity in both directions. And now we should see we have an entry in the ARP table of router 10, which is this MAC address. So what does that address correspond to? Is this going to be router 5 layer 2 address, or maybe the address of the ASA? So the answer here is that this is going to be the layer 2 address of the ASA. We can take a look at the interfaces and MAC addresses specifically. So D48C 6E to F, this is this one, which I believe is going to be interface Giga 1, which is our outside. So once we have configured the translation, what ASA did internally is that it started acting as if it is it started acting as this IP address belongs to itself. It started treated this translated address as its own, meaning that the proxy ARP feature is enabled, and ASA for the ARP request packets received from the clients connected on the outside, it is going to be replying that, saying that this .55 address is actually me at layer 2. So this is why router 5 was able to populate its ARP table with an entry for this translated address, and it now thinks that to send the frames to 55, it is supposed to send the frames to the ASA, to the outside of the ASA. So ASA is getting the frames and is able to perform a detranslation. It has an XLate entry. It gets the packet with this destination. It knows that it corresponds to this address on the inside. This is part of the local subnet, so I have to take a look at the CAN table to find a matching entry for whatever corresponds to 172.10.45, which is this MAC. So it knows that the frame should be sent to the inside after detranslation. So this is what happens when both the client and the pool, the address pool used involved in the translation, are part of the local subnet. Now, it is also possible to disable this default behavior of the ASA, which is proxy ARPing for translated addresses that are part of the local pool. We could go back to the configuration of our NAT over here to the object, and instead of using just this syntax, we could also add this option, no proxy ARP. So let's try to think what's gonna change with the feature being disabled for this translation. So when I go to router 10 and shut the interface down to clear the ARP cache, then we'll bring it up. And we will now try to once again reach router 5's translated address. What's going to happen now? 172.10.40.55. And let's also enable debug for ARP on both the ASA and router 10. And I'm trying to reach the translated address of 5. It says I'm sending requests via my GigaO2, but I don't get anything back. The entry here is going to be now incomplete. Because now when the ASA, when ASA sees the ARP request, which is a broadcast, so it gets the request, since we have disabled the proxy ARP feature for 172.10.40.55, and this is the address in question in the ARP packet, in the ARP frame, it doesn't reply to 10 to tell it that I'm the guy you should be sending the packets to for this address locally. So 10 is not able to perform the resolution, and we don't have connectivity because the control plane is not built. So a workaround, if this was a layer 3 device that was doing the translation, you could simply create a static route and redistribute it to the routing protocol that you have enabled internally. In our case, this is Transparent ASA, so we cannot enable routing protocols. The only thing that we can do in this case, with proxy ARP disabled on the ASA, would be to configure our upstream device, so router 10 in this case, with a static route for 172.10.40.55. This must be something longer, the subnet or the host route. This subnet here, in this case, this is a host route. This must be something longer than the connected /24 interface, so it is going to be a preferred route to send frames to this subnet or just this address. So in my case, I simply put the /32, and the next hop is gonna be what? Is it gonna be the ASA, or is it gonna be my final destination, so 5? So we can do actually both. You can point with this route, you can point directly to the ASA, or you could point to 172.10.40.5, because in both cases the ASA is gonna get the frame. And it's only needed for the ASA to get the packet so it can perform the translation. Now, the recommended way of doing things like that is to point directly to the ASA, which is going to have one advantage over the other method. Namely, if this was a device somewhere in this subnet with the same address, you would make sure that it is the ASA what is getting the frames and is able to perform the translation, so the return packet is sent to the originator. So we will point to the ASA 172.10.40.40, and with this configuration, it's like I'm telling 10 that to get to 172.10.40.55, we will be sending the package physically to the ASA. So we see that we have connectivity because ASA is getting the frames and it is able to perform the translation. Okay, so let's remove this route. let's remove this configuration from the ASA. Now object network. So no NAT, no objects. And let's now move on and think about this second case, which is when the source is going to be part of the remote subnet. So I don't want to change the address of the local device. We will be now changing an address of router 5, but the loopback interface, 10.5.5.5. There is going to be one additional thing that we will have to take into consideration when we want to change addresses that belong to remote subnets. So let's take a look at this. So we will go to the ASA and start our configuration in the exact same way as previously. So the object is going to be type of network. This time I'm going to call it R5 loop. 10.5.5.5 is the original address. What is my translated address? Let's go for 172.10 for the 105. So remember that this is the local pool, what we are focusing for the translated addresses. In our case, pool is just a single address, but it doesn't really matter. So what's going to happen now? So the translation is in place. Before I send the packets, let's think let's think what's going to happen before we take a look at this on the command line. So let's go back to the topology here. Now let's think what's going to happen when a 5 sends the packet from the loopback with a destination of router 10. So the source is going to be 10.5.5.5, and layer 2 source is going to be MAC address of router 5 of this interface. So ASA is going to get the frame, it's going to look into the XLATE table. It sees that there is an XLATE entry that tells it to change this source before the frame is switched to the outside to be something else. So on this side of the network, we should see something like that. The source is going to be modified 172.10.40. I said 105. But in addition, what the ASA is going to do is that to recompute the checksums, because the addresses has changed at layer 3, it is going to recompute the checksums, and it is going to re-encapsulate the frame with a modified MAC address in the source. It is going to basically change it to be the ASA's MAC address, in this case MAC address of the outside port. So normally if this was a layer 3 device, as I said previously, when you do the translation on that type of box, the changes done at layer 2 are not part of the NAT process. They are part of a regular switching, routing and switching logic, which is when you switch the packet to a new link, to a new local network, you will modify the source, you will change the source address to be you. So this is when you are doing the re-encapsulation to a new, before the frame is sent onto a new link. This would normally not happen with a transparent ASA, because it bridges the frames, it doesn't route them, it doesn't have to re-encapsulate the frames. They are supposed to be part of the single local network, so there is no need to change the addresses. But when it does NAT, it is gonna technically also change layer 2 source of the frame. But I only mentioned this for completeness. It doesn't really, it's not really important to the process. Because when, as we will see later, when 10 is going to reply back to the changed address to 172.10.40.105, it is still supposed to do the route table lookup and the ARP table lookup, and it is going to reply to the, in this case, to the ASA, with the proxy ARP feature being on. So 10 is able to get the frames. We should see this on the command line. Let's say a debug ICMP package. Let's go to 5. Let's debug IP ICMP as well. And let's try to send, let's say, 2 packets router 10. But we will source them off our loopback. So I'm sending the packets with this source. On the ASA, we should see the translations. We see that we have the translation. We even have a detranslation. Now 10 is getting the package, and it is sending replies back to 172.10.40.105. So to detranslate the address as we would expect. But we don't get the replies back on 5. So there is a problem with this configuration, and it is now related not necessarily to the NAT configuration, but more of to the routing behavior of the ASA. Because when 10 replies, as we saw, it is going to reply to 172.10.40.105, for which the ASA, same as previously, since I did not disable the proxy ARP feature, the ASA is proxy ARPing for this address as well. So the frames will be physically sent to the ASA. So there is so in the data plane between 10 and ASA 4, everything is fine. The control plane was built. ASA is getting the frames, the reply package. So the question is, what happens on that part of the network that causes router 5 to not receive the replies? And this is, as I said, related to the routing behavior of the ASA. Because when the ASA gets a packet for which it has an XLate entry, which is this one, it gets the frame with this layer 3 address. Even that it is a transparent firewall, it still looks at the XLate because it is possible to configure ASA, transparent ASA for NAT. So it still does that XLate lookup, and it sees that it has a match for the packet. Destination is 172.10.40.105. This is part of that XLate, and the XLate tells the ASA that the packet, after detranslation, should be sent to 10.5.5.5. And it even tells it what is the egress interface for the packet. But since 10.5.5.5 is not part of the local subnet, the ASA needs to know what is the next hop that it is supposed to use to get to this subnet, 10.5.5.0/24. And its routing table is blank. So we still need to add, for situations like that, when the sources of the translations, the clients, are part of a remote subnet, we still have to add a route on the ASA so it knows how to get to those devices. So we have to fix it at a route via the inside interface for this subnet, where the next hop is going to be obviously router 5. So with this in place, we should see that we have connectivity here. Okay, so now the two remaining cases I would like to go over. This is going to be a non-local pool with, once again, the local client and remote client as the source of the translation. So let's quickly take a look at this first sub option, the local client. And again, I will change the address of router 5's fast Ethernet 0/0 interface. So let's just remove this translation. And let's create a new object. Router 5 new, 172.10.45. And I said that this time the pool is going to be something that is not part of the local subnet. So let's go for 55.0.0.5. And this is a static translation. Okay, so what's going to be different now? If you think about it, about the traffic flow, so for the direction of the translation, so from 5 to 10, nothing really changes from the previous case. Well, of course, except of the addresses. So now the source is gonna be, I will simply say router 5, which is that 172.10.45. The source after translation is 55.0.0.5. 10 is gonna be able to, should get the frames. We can quickly test it. So I will try to reach router 10 from 5. And it is replying as expected to 55.0.0.5. Now, the problem now is that it's router 10 that doesn't know how to get to 55.0.0.5. So this is what normally happens when you configure a non-local pool that is for which the devices don't know how to reach it. So the two solutions are, at least two solutions, if this was a layer 3 device that was doing the translation, would be to either redistribute this subnet, add a static route on the device, maybe a loopback that is emulating this postnet subnet, and redistribute this network to the IGP, or on the upstream device, such as router 10, simply tell it about this subnet and maybe redistribute over here. In our cases, we have just two devices involved, so I will add a route for this device. And again, we can either point to the ASA with the next hop, or we can point to router 5. The recommended option is going to be to always point to the ASA. So let's go ahead and do this. 172.10.40.40. And when I try to ping once again, we see that we have connectivity. So just one additional thing that we have to consider comparing to the previous cases was that we just want to make sure that the devices, the upstream devices, they know how to reach the pool. And they are supposed to point to the pool, for the pool, to the ASA. And the final case is when we will be changing the remote networks, remote addresses. So we definitely have to add a route on the ASA. It's basically, this last option, this is basically a combination of what we did so far. We have to add a route on the ASA. And the second thing would be to make sure that upstream devices that they know about the pool. So this is something that we have configured on the ASA in the previous case. This is something that I have configured a minute ago. We should see that this is going to work when I just simply configure the translation on the ASA. So let's say object network host 10.5.5 and then the translation. Let's go for 105.115 and then test it from router 5. 172.10 for the 10 from my loopback. Actually, I changed the, I should have used the same pool because now it's router 10 that doesn't have a route. So maybe let's go ahead and do this. So let's go for the 55005, what I want to use over here. Let's take it out. And we see that we have connectivity. If you're looking for any type of other training from us, from iPexpert, you can always look at YouTube and our blog. There's going to be some freebie lectures on YouTube and some blog articles on the blog website. And for any other stuff, like just information about the new incoming products, some promotions, you can always follow us on Twitter and Facebook. Thank you for watching.